Hello, everyone. So, electronics and software is the key innovation driver for automotive, and it will become even more important in the future. And especially automotive SoC design is key to enable the next generation automotive systems. So in my talk, I will touch on ADAS and autonomous driving, covering the latest infotainment trends, then talk about automotive SoC design, and last but not least, also talk about system design, analysis, and verification. So let's have first a look at the overall automotive market. So what we can still observe is a strong growth for automotive semiconductors, and 12.3% is really very nice in this space. And there's a drive towards leading edge process technologies, so 16 nanometer, 7, 5 nanometer, I will talk about that later. There's also, because of that, a supply chain disruption. So there are the OEMs directly working with the semiconductor vendors. The tier ones are squeezed in the middle and try to find their way. And there's also still a shortage of semiconductors in the automotive industry, and that also triggered some activities in semiconductor design at the OEM. If we talk about autonomous driving, there's still a lack of adequate SoCs that can be really used for commercial vehicles for autonomous driving, so there's a lot of design activity in this space as well. So the industry is responding to the supply chain disruption. OEMs and tier ones are starting with SoC design. Traditional semiconductor companies, for instance, out of the consumer market, are entering the automotive market, and there are also lots of startup companies providing sensor solutions and other systems. So what are then the automotive key challenges that we can see? First of all, there will be a change in the EE architecture, so electric and electronic architecture, which causes a whole chain reaction of other technology changes. Then hardware-software complexity is growing rapidly. For autonomous driving, scalability is very important. How can you scale an autonomous system down to an entry-level car? Compute performance due to AI, but also sensor processing, is rapidly increasing. Then we have processors running in the gigahertz range, causing lots of EMI problems. ADAS compute platforms are usually today water-cooled systems, so thermal issues, power consumption in combination with electric vehicles is also a big issue. And of course, we still want to make sure that a car is very safe and reliable for 15 years. So that needs to be addressed as well. And then we have the connectivity to the cloud, 5G, Car2X, and so forth, and in-vehicle networking. So we've been investing heavily in various key automotive areas. So one is ADAS and autonomous driving. And if we look in this area, then we can see there are the designs, the chip designs with the most advanced nodes. So lots of companies are doing today already 5 nanometer designs. But we also see other process technology nodes as well. And this is also the place where a lot of the AI processing is happening, so the compute demand is also the highest in this domain. The other space that used to have the highest complex chips is infotainment. And infotainment is maybe, from a technology point of view, one node behind ADAS. And there it's also all about features, connectivity, scalability. Also some ADAS functions are integrated in the infotainment SoC. So driver monitoring systems, digital mirrors, and so forth. So all these things are part of an infotainment system. Across those two domains, functional safety is paramount. It's table stakes. So for infotainment, we can see already ASIL B type of chips. But for ADAS, it could be, in terms of the safety requirement, even a higher ASIL level. So functional safety needs to be verified and proven, and chips needs to be certified. And that's also a very complex challenge by itself. I will talk about that also a little bit later. And last but not least, system design. So we need to make sure that these complex chips are also working in the system context. And so that means I put the chips on a board and I move from a traditional board design to high-speed design due to Ethernet, but also other automotive standards. EMI and thermal, I mentioned that already, but also electromechanical co-design is very important. So let's get into the first domain, ADAS and autonomous driving. So the OEMs currently developing what we call a zonal architecture. And a zonal architecture basically includes zonal controllers. Those are the green boxes. And the zonal controllers are configurable or programmable devices that can be used for various functions like vision processing, radar processing, could be also audio processing. And these zonal controllers are connected via high-speed Ethernet backbone to the central CPU. And here the blue boxes, as you can see, it's a redundant system. And there are also intelligent gateways included, and the gateways are routing the data between the zonal controllers and the central CPU. And I mentioned in the beginning scalability, and depending on your sensor stack that you're operating in a car, you can basically scale the architecture by adding or removing zonal controllers. And the zonal architecture is in particular interesting for the OEM because it enables an ECU consolidation. And remember, in the past there was one ECU, one function, and now we have high-performance ECUs that are doing multiple functions, and so you can reduce the number of ECUs. So Cadence provides a wide range of DSP processors that can be used for audio and voice, for radar, lidar, communication, for vision, and for AI processing and other functions, and I will cover that one a little bit more in detail. And these DSPs are optimized for very specific tasks. And because of this optimization, the DSPs are more efficient in terms of compute performance, power consumption, or silicon area, and they can work in tandem with a CPU core, a quad-core processor, for instance. And so you can offload from a CPU to the DSP those functions. So if we look into ADAS, there are basically two use cases. So one is the typical ADAS system, could be a smart camera system, it could be also a radar system, or the autonomous car. For ADAS systems, we see in terms of the compute performance requirement something between 0.25 and 4 TOPS. But for autonomous cars, we see already hundreds of TOPS in terms of performance. In order to address this wide range of compute requirements, we do provide for all our DSPs, in this case it's our vision DSP, we provide different performance grades of this processor that allows you to scale your function exactly to the requirement. In addition, if the compute performance of, for instance, a vision DSP is not sufficient, you can combine our DSPs with an AI hardware accelerator. And these hardware accelerators can be also scaled up to higher performance levels. And at the end, you can build out of a standard DSP, an AI hardware accelerator, a multi-core system that allows you to have a very high performance compute engine for various tasks. And so AI is very important, and the designers are using, the software developers are using different development environments. But the most important thing is, how can you get from your neural network that you have developed in TensorFlow or in Caffe in an automated way, very fast on your target hardware platform, and test drive whether the function is working correctly. And for that, we provide extensor neural network compiler that is doing the quantization, the optimization. So it takes your neural network and generates the code for our Tensilica processors. So talking about AI, so we provide in our baseline processors a certain ISA extensions, so specific data types optimized for AI, so you can run already AI functions on our standard processors. And we have actually at our booth various demos that show these AI features. But if that performance is not enough, then you can add a neural network, a hardware accelerator, an AI engine to boost the AI performance. So that's our standard Tensilica DSP plus a hardware accelerator. In addition, you can scale up the system, standard processor, plus a multi-core AI engine. That's what we call DNA, Deep Neural Network Accelerator, to achieve a much higher performance. So in addition, what we have also seen from automotive is that requirements are ever increasing, and especially for safety. So maybe for 2 years ago, ASIL B was fine for radar, but then people are expecting already an ASIL D type of radar sensor. And so we have added to our Tensilica product portfolio a core, what we call extensor flex lock. So you can create a dual core lockstep architecture to achieve, for instance, an ASIL D safety level. Security is another big topic in automotive, especially for autonomous driving. So people are building on an SoC what we call a security system. And in that case, we have developed an extensor LX secure mode, which allows you to create a root of trust system to enable a safe boot of your system, do some security key authentication with Tensilica and other features. On the radar side, we have added to our highest, so we have about 6 different radar cores, but the B10 and B20 are our highest performance radar cores, and so you can combine now the radar cores with a dual core lockstep core for highest safety levels. And last but not least, we have added dedicated floating point DSPs, and we saw, for instance, in infotainment that some audio functions are done with floating point processors, and so that's why we have created an optimized floating point DSP to address this requirement for minimal area and lowest power consumption. So if we look now at this level 4 driving platform with our Tensilica portfolio, so we can address the camera system with our vision processor, the radar system with our Connex processors, the Lidar system also with the Connex processors, and the ultrasound sensors with our Hi-Fi processors. And the sensor fusion can be done with a Fusion G6, for instance. So that means with Tensilica you can fully address an autonomous driving chip. And we have actually built such a chip, and we operate a test car in Japan together with the University of Nagoya that has a Lidar sensor, a smart camera, using digital maps and doing a sensor fusion. So let's switch gears to infotainment. So for infotainment, we all have meanwhile seen those cars with those multi-cluster displays, huge displays. Another trend is Dolby Atmos to provide an immersive sound in a car. Could be for music, but it could be also for autonomous driving that you have exactly the sound coming from the direction where a sensor is eventually detecting an obstacle or something like that. On the safety side, classical mirrors are being replaced by camera-based mirrors, which are much smaller and provide some nice features. Driver monitoring systems are becoming standard, and also in-cabin passenger detection systems becoming more and more popular, and those systems could be radar-based but also vision-based. And last but not least, connectivity. So what does that mean for Tensilica? So if we talk about infotainment SoCs, there are currently 5 high-end SoCs on the market. In 4 out of 5 SoCs is Tensilica Hi-Fi included. And the reason for that is because we have a huge software partner ecosystem that provide all kind of functions. It could be active noise cancellation, it could be a codec for AAC, it could be a voice trigger, voice recognition, and so forth. So there are lots of software functions off the shelf available. And of course, we also have an AI-based voice recognition available with Hi-Fi. In addition, we support all digital radio standards, also running on Hi-Fi. So that means all these nice functions that you know from your car are running on Tensilica, so they are offloaded from the main CPU towards the Tensilica DSP. One of our recent examples was a collaboration between Samsung, Harman, and Audi. So it was the first infotainment chip that Samsung developed. It's an 8-nanometer chip, very complex. And so this chip uses 4 Tensilica Hi-Fi 4 DSPs to do all the audio processing in the car. And it's combined with a neural networking engine from Samsung. And the interesting thing about this chip is because it was a complex development that in parallel we have created a virtual platform to simulate the chip and the software on top of it before the silicon was available. So that brings me to automotive SoC design. So these complex SoCs enable a lot of functionality. And if we look into the in-vehicle networking, that's right now a little bit of a bottleneck to enable even more functionality. And if we look now into those different PHY technologies that are available, so automotive Ethernet will be the dominant network technology within a car for most OEMs. Just make this bold statement. And so that means the connectivity between the ECUs and the central ECU is based on Ethernet. And here what we are currently seeing is, so 1 gigabit Ethernet is in production. The next speed grade will be a 10 gigabit, and down the road there will be a 25 gigabit. But the interesting field right now, where there are lots of discussions going on, is actually the connection between the sensor and the zonal controller. And there are various options as a PHY technology that can be used. So you could use PCIe, so a SerDes technology, which provides a very low latency and high bandwidth. You can also use MIPI technology, and the latest incarnation of MIPI is the MIPI A-PHY, which provides also very high data rate and 15-meter cable length support, which is important, and also automotive Ethernet. So that means if you want to design a complex SoC, you cannot design all these functions and interfaces and processes from scratch. So you need to use IPs that are provided by, from a company like Cadence as an IP provider, to have a kind of a Lego system to put all these IPs together on a chip. And in addition to all these interface standards, you need to have a safety certified IP. So all our IPs are certified as an element out of context ASIL B and can be used for automotive chips. In addition, we support for the PHYs also ACQ 100 grade 2 technology. So at the end, what you would like to eventually put together is an autonomous driving SoC that looks like this. So there are 5 main computing domains. So there's a central CPU cluster, but in addition, there's a vision processing domain, and in addition, there's a neural network engine, a safe and secure subsystem, and other things as well. And at the bottom, you have about 20 different interfaces to provide all the connectivity that the OEMs are currently using and requesting. And so this is then a pretty complex device. So far I talked a lot about SoC design, but we also need to make sure that the SoC works in the system context. And so we need to design the system, analyze, optimize the system, verify the system. And so Cadence provides flows and tools for chip design. We provide the leading tool worldwide for package design. We also provide various solutions for RF module and RF board design. We provide solutions that allow you to analyze an ECU, including the chassis, so ECU and system. And we provide a simulator to simulate the connectivity from a PHY to the board, to the connector, to the cable, to an inline connector, to the next ECU, so the full physical channel. So let's move into the first part of the chip design and just focus on digital verification as one example. So for digital verification, you can develop, first of all, a virtual platform of your system, similar to what I've mentioned before for the Samsung Exynos chip. So before you do any chip design, you do some performance analysis on a virtual platform. Once this is working fine, you can start with your RTL design, and you can use an emulation technology to simulate low-level software together with your RTL on an emulator. If this is working, you can recompile the design and put it on a FPGA-based prototyping system. So at the end, what you can do is, if you take our new virtual platform system, which is called Helium, so you have a graphical platform assembly. You leverage a virtual model library with standard building blocks or ARM processor models or Tensilica System C models and so forth, and you put together your platform. And then you can mix the virtual platform with our emulator or our FPGA system, and you can do a hybrid simulation. So some models are described in System C, other models are available in RTL, and other models are already synthesized to a gate-level netlist, and you can simulate the whole thing together. And the idea is for the software developer to validate software, to develop software before the first silicon is coming back from the fab. So I mentioned also in the challenges functional safety. And the problem that we saw in the past is there are lots of FMEDA tools, FTA tools, HARA tools, so all these tools where you analyze the safety of your system, but unfortunately all these tools are disconnected from the chip design flows. So that means all the failure rates that you estimate in this FMEDA tool are a little bit off from the reality. And so what we did is we have developed this Midas safety platform and connected it to our IC design flows. So that means we can import the chip design into Midas, and if we import the chip design, we know exactly what are the building blocks of my design, what is the area, the number of transistors, the number of gates, and then I can much better or much more accurate estimate failure rates. And in particular, since I set up the failure modes in Midas, I know exactly how my base failure rate gets distributed across the different failure modes. So that means with this system, we enable an FMEDA-driven digital safety design and verification, but also an analog safety design and verification. Last but not least, system design. So Clarity is our finite element tool for electromagnetic analysis. So you can have, so this picture shows a stacked PCB. We can simulate it and we see exactly the electromagnetic field across those PCBs. And so we can model these systems and analyze these systems. That's a near field simulation, and for far field simulation, we have Clarity with our new transient solver, and we can also do a far field simulation, interference of a mobile phone to any system and so forth, and we can also validate the system in terms of the EMI, EMC robustness. In addition, we have security for planar technologies, for board design, to analyze those systems in terms of signal integrity, but also power integrity. And last but not least, we can use the finite element solver and combine it with our thermal tool, which is called Celsius. And so we can simulate then the cooling device, the solids, in combination with the thermal heat dissipation coming from a chip in one simulation. So that's an electrothermal co-simulation. So as a summary, so I mentioned all these challenges. So as I said, these zonal architectures are driving a lot of changes in automotive that goes across the board, processing, networking, and so forth. And so we provide for all these things solutions. But if there's one message I want to close my talk is SoC design will become key in the future to differentiate your products in automotive. And with that, I'm pretty much almost on time. Thank you very much.